Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is elementary row operations and matrix spaces. What do elementary row operations do to row space, column space, and null space of a matrix? So let's start by remind you what those matrix spaces are. So if you start with an M by N matrix, you can think of it as consisting of M rows or N columns. The R1 through Rm are the rows, and each of them are an element of Rn. C1 through Cn are the columns, and each one is a column vector with M entries, so it's an element of Rm. But if you look at the rows, then the row space of A is the span of those M rows. There's M rows, but each of them are in Rn. So this row space is actually, because it's the span of a bunch of vectors, it's a subspace of Rn. Likewise, the column space is the span of the columns, is all the linear combinations, all the vectors you can get, all the column vectors you can get by finding linear combinations of the columns. And that will be a subspace of Rm. Each one of these columns, there's n of them, but each one of them has m entries. It's a long column with m entries. And if you find linear combinations, you find the column space. Among the elements of the column space are the columns of the matrix, but there's more than that. You can add two columns. You can multiply a column by 5 and subtract 3 times the other one. So all of those kinds of vectors you can get is in the column space. Finally, the null space of A is the set of solutions to the system, the homogeneous system of linear equations AX equals 0. AX equals 0, where X is a column vector of unknowns, is a homogeneous system of linear equations. And the set of solutions to that is called the null space of this matrix. What we are also interested in is what's row equivalent. Row equivalence means that you have got two matrices that are the same size, M by N, and you say that one is row equivalent to another if you can get from one to the other by elementary row operation. Multiplying a row by a non-zero constant, switching the place of any two rows you like, and adding to any given row a scalar multiple of another row. Those are the three elementary row operations. And if you can start with A and do various kinds of elementary row operations and get yourself to B, we say A and B are row equivalent. And the subject of this lecture is to see if you do those elementary row operations, what happens to row space, column space, and null space. And we will get to that momentarily. There's another way of thinking about row equivalence. Instead of saying do elementary row operations, you can say that you can take your matrix and multiply it by elementary matrices. What's an elementary matrix? It's a matrix that you get from the identity by one elementary row operation. And the purpose of that elementary matrix is that if you pre-multiply my matrix by it, if you have a matrix A and if you put E on the left and multiply them, then that elementary row operation happens. So elementary matrices do elementary row operations for you. Look at the video about elementary matrices if you're not familiar with them. To say that A and B are row equivalent means that you can start with A and do elementary row operations and get B. But instead of doing those elementary row operations, you can multiply by elementary matrices. E1 times A, that does one elementary row operation. E2 times E1A does elementary row operation on E1A, and so forth. So there's K elementary row operations, E1, then E2, all the way till EK, that are being applied to A, and that's giving us B. So this is another way of saying when two matrices are row equivalent. If A is row equivalent to B, then B is also row equivalent to A. And intuitively, that makes sense. If you can do row operations from A to go to B, you can undo those and go from B to A. And undoing an elementary row operation is also an elementary row operation. We talked about these in the video on elementary row operations. It's not very hard to figure it out anyway. In fact, you can do that by multiplying on the left this blue equation by EK inverse. And when you do that, on the right, EK inverse cancels EK. So that means that you peeled off EK and moved it to the other side, but you paid a price, you made it EK inverse. Then you multiply by EK minus 1 inverse, EK minus 2 inverse, all the way till E1 inverse, And what you will get is that if you apply these elementary row operations, remember the inverse of an elementary matrix is an elementary matrix, then you get A. So you can start with B. And in fact, the undoing of the same row operations in the opposite direction goes from B to A. That's something to be expected. So that's what row equivalent is. So again, what we're going to do is we're going to say two matrices are row equivalent, meaning that you can get from one to the other by elementary row operations. What happens to the null space, the row space, and the column space? So let's start with null space. So if A and B are two n by n matrices and assume that they're row equivalent to each other, so again, you can get from one to the other by elementary row operations, then their null spaces doesn't change. Recall what a null space was. The null space was the solutions to AX equals 0. And so what we're saying is that the solutions to AX equals 0 are the same as the solutions to BX equals 0. If you've solved the system of equations using Gauss-Jordan elimination, or what I'd like to call the method from the 9 chapters, then you have used this theorem because of the fact that you've assumed that when you do elementary row operations to a matrix, the system that is associated with that matrix, solutions to that, does not change. But what we're going to do now is give a formal proof of that, something we didn't do in an earlier video about systems of linear equations. We gave an intuitive argument that because every elementary row operation is undoable, no information is lost, and therefore the system must have the same solutions. But now I'm going to give you an actual formal proof. So A and B are row equivalent. So again, that means that you can start with A and multiply A by elementary matrices. That's the same as doing elementary row operations, and get B. How am I going to prove that null space of A is the same as null space of B? You have two sets. You want to show they're the same. You have to show that every element of null space of A is the null space of B, and every element of null space of B is a null space of A. So let's start with C and assume that's in the null space of A. And C is not a number. C is a column vector. What kind of a column vector? A column vector that when you multiply by A, you get 0. We have C in the null space of A. We want to show that it's a null space of B. And what we know is that A times C is 0. That's what it means to be in the null space of A. So we want to show that C is in the null space of B. How do you do that? A vector has walked through the door and claims to be in the null space of B. How do you check that? Well, you find BC and see if it's 0 or not. B is these elementary matrices times A times C. So that's what BC is. But AC itself is 0. Now, if you take those elementary matrices and multiply by 0, you get 0. So if AC is 0, BC is also 0. And therefore, if C is in the null space of A, C is in the null space of B as well. So we have proved one inclusion, that null space of A is in null space of B. But the other direction follows the same. Why? Here we use the fact that you can go from A to B by elementary matrices, but you can also go from B to A by elementary matrices. And so you can make the same argument and show that the null space of B is also in the null space of A. And if we have those two inclusions, then the two null spaces are the same. So this was a formal, precise proof why when you start with a system of equations and you do elementary row operations to the augmented matrix and then solve the resulting system, you always get the same solutions as before. You don't lose any solutions, you don't gain any extra solutions. And this is something that we have been using, but now we have a formal proof to. Let's look at a quick example. So A here is a 3 by 4 matrix. And what's the null space of A? Well, how do we do that? Well, instead of finding the null space of A, we find the reduced row echelon form of A and find the null space of B. B is the reduced row echelon form of A. A and B are row equivalent. Finding the null space of this guy is the same as solving Bx equals 0. These columns each are associated with a variable, X, Y, Z, and W, because we have 4 columns, we have 4 variables. The 2 columns that do not have leading ones, in this case, Z and W, those are going to be few variables or non-basic variables, and they can be anything you like. And then you can solve X and Y in terms of them. And solving them is very easy because this first row is giving us an equation. It's telling us X plus 4Z plus 5W equals 0. And so X is just going to be minus 4Z minus 5W. And this one says Y plus Z, minus Z minus W is 0. So Y is Z plus W. Therefore, we can write down the solutions. Again, Z and W, I put them arbitrary real numbers R and S, and then I solved X and Y in terms of them. So the null space of A is the same as null space of B, and is that. It was not as easy to find it from A, but it is very easy to find it for the reduced row echelon form of A. And presumably you have done this before. Again, if you have not, go to the video on systems of linear equations. Having this description of the null space, you can write a basis for it. So you put r equals 1 and s equals 0, and then you put s equals 1 and r equals 0, and you get two vectors, minus 4, 1, 1, 0, and minus 5, 1, 0, 1. And if you multiply this by r and that one by s, then you get the typical element of the null space. So these two span the null space, and they're linearly independent, and so they're bases. I wrote transpose because I usually like to think of null space elements of the null space as column vectors, although I didn't do that over here. If I just want to tell you what the set is, I don't really care if it's a subspace of R4. I don't really care whether or not I wrote things as row vectors and column vectors, but when I'm thinking of them as matrices, then I like to think of null space as column vectors. And the nullity of A, which is the dimension of the null space, is 2 because there's two elements in the basis. Okay, now let's move on to the row space. So we have a corresponding theorem for row space. If you have two m by n matrices, and if they're row equivalent, again, that means that you can get from one to the other by elementary row operations, then the row spaces does not change. So let's prove that. So again, what we have to do is prove that every element of the row space of A is in the row space of B, and every element of row space of B is in the row space of A. And again, if you can prove one of those, the other one follows, because if A is row equivalent to B, B is row equivalent to A. In fact, we will do one more thing, which is instead of saying that A is row equivalent to B, only focus on the case where B is obtained from A by one elementary row operation, not by a sequence of them. Well, if we can prove that row space of this matrix B is the same as the row space of A, then it will be true for all row equivalent ones. Because if another matrix is gotten from A by 10 elementary row operations, well, the row space of A is the same as the row space of the second one, and the row space of that guy is the same as the row space of the third matrix along the way that we get, and so forth, so we get to that final matrix. So it's enough to prove the theorem for the case where you get from A to B by one elementary row operation. Let R be a row of B. Then R is either a row of A, because when you did one elementary row operations, plenty of the rows of A don't change. In fact, even if you do the first type of elementary row operation, when you switch the rows don't change. The rows are in a different order, but it's the same rows. So that row of B that you're looking at could be a row of A. If it's not, what would it be? It's a linear combination of rows of A. Why? Because you multiply a row by a constant. Well, you get a linear combination. Or you take the row that you're going to change, and what you do is you add a scalar multiple of another row to it. Again, you're finding a linear combination of rows of A. But linear combinations of rows of A are the row space. So whatever this row of B is, it's in the span of the rows of A. It's a linear combination of rows of A. But that's exactly what the row space of A is. So rows of B are in the row space of A. That's not the same as saying that the row space of B is in the same as row space of A. Row space of B is more than the rows. It's linear combinations of the rows. But that's no big deal, because if all the rows of B are in the row space of A, then the span of all the rows of B will also be in the row space of A. Why is that? Well, because if you have a bunch of vectors in a subspace, the row space of A is a subspace. And then if you find the span of those vectors, linear combinations of those, it can't get out of that subspace because the subspace is closed under linear combinations, under addition and scalar multiplication. So if rows of B are in a row space of A, the span of the rows of B are also in this row space of A, but the span of rows of B is the row space of B. So we just proved that row space of B is inside row space of A. But again, if you can get from A to B by a single elementary row operation, you can get from B to A by a single elementary row operation also. And therefore, row space of A is also a subspace of row space of B. And since we have both inclusions, the two row spaces are the same, and we're done with the proof. Let's go back to our matrix, the 3x4 matrix A, and let's see how we would find its row space. So again, if you want to find the row space, that means the span of the rows. So you could just start with the rows of A and then try to see, okay, that's the spanning set. See if you can find a basis by going through them and then throwing out anything that's a linear combination of the ones before. Or you can find the reduced row echelon form of A, and you can say that the row space of A is the same as row space of B. It's going to be the span of 1, 0, 4, 5, and 0, 1, minus 1, minus 1. There's only two of them. They're linearly independent, and that's a basis. When you have something in reduced row echelon form, all the non-zero rows are going to be linearly independent because they all have a 1 in a place where everything else has a 0 there. So you can't write one as a linear combination of the others. So finding a basis for row space of a matrix in reduced row echelon form is actually very easy. Row rank of A is 2. Row rank is the dimension of the row space. Spoiler alert, later we will show row rank and the column rank are the same, but we haven't quite done that in this series of lectures. Now let's move on to the column space. So far we saw that when you do elementary row operations, the null space doesn't change, the row space doesn't change. And you might think, if you don't think about it too much, well, maybe the column space doesn't change either. That's not the case. And intuitively, that actually does make sense because when you do elementary row operations, you're moving rows around. And when you're moving rows around, the row space doesn't change. But when you're moving rows around, the columns actually change quite a bit. Every entry is affecting things in its own column, but that one column you can change quite a bit. So here's A, for example, and here's its reduced row echelon form. This is the same matrix we've been seeing over and over again. And are their column spaces the same? Well, they're not the same because 1, 0, 2 is in the column space of A. How did I know that? Well, because that's one of the columns. That's actually the first column of A. If you're a column of A, you're in the column space. But column space is more than just the columns. It's the linear combination of our columns. But 1, 0, 2 is in the column space of A. Is 1, 0, 2 in the column space of B? No. Why not? Well, because if you look at the columns of B, they all have zeros in the last coordinate. There's no way to find a linear combination of columns of B and get a 2 as the last coordinate. So this vector is in the column space of A, but not in the column space of B. So the column spaces are not the same. Is all lost? No, all is not lost. In mathematics, we sometimes take things too far, but we usually don't settle for, well, that didn't work. We try to figure out, well, what does work? And something you might notice, this is not something that one would immediately notice, but it's a pattern that's there. For example, 4 times the first column of, this is 1, 0, 2 is the first column of A, minus the second column of A is equal to the third column. So in other words, I took the columns of A and I wrote some linear combination of them. 4 times this minus that equals that. I wrote a linear relations between the columns of A. And if you now notice, the same linear relation is true about column space of B. So 4 times the first column minus the second column is the third column. So 4 times this minus that is that. 4 times this minus that is that. And what are these thises? They're the corresponding columns of A and B. That's the thing that's actually true about column space, is that the column space changes, but the relations, the linear relations among the columns does not. And that's a very crucial point. Think about that in more general, why that would be. So A and B are m by n matrices. I'm actually trying to prove the theorem before stating it. So A and B are m by n matrices and assume they're row equivalent to each other. So finding reduced row echelon form is one way of finding a matrix that's row equivalent, but you don't have to find, but A and B can be, neither one of them can be in reduced row echelon form, and yet they be equivalent. A has some columns. I'm focusing on the columns. So it has n columns. Each one of those columns has m entries. So C1 is not a number, is a column vector. And B also has n columns. They're very different columns, C1 prime, C2 prime, Cn prime. And I want to know what the relationship among them is. So assume that I have some linear relation between the columns of A. And any linear relation, you can bring everything to one side and write it as a linear combination equal to 0. So alpha 1 C1 plus alpha 2 C2 all the way till alpha n Cn is 0. So assume we have that. Now you might say, well, we might not have that because those might be linearly independent. Well, if they're linearly independent, then that means that the only way you can do this is when alpha true alpha n is 0. Okay, well, that's fine. But otherwise, this is what I've got. Okay, and what am I going to do with that? Well, I'm going to ask you the following question. I'm going to take those scalars, alpha 1 through alpha n, and I'm going to make a column vector out of it, and I'm going to call it D. If you don't like calling it D, call it Fred. But that's the column vector that I like. And then what I'm going to say is that what happens if you multiply A by D? Now, A is an m by n matrix. D is a column vector. How do we multiply a matrix by a column vector? We had a whole video about this, about another way of thinking about matrix multiplication. If you have a matrix and you multiply it by a column vector, one way to think about it, the definition would tell you take the rows of A and find a dot product by D. But the way we often like to think about it is that when you multiply a matrix by a column vector, what you get is a linear combination of the columns with the scalars coming from the column vector. So in this case, the columns of A are C1 through Cn. The scalars are alpha 1 through alpha n. So what do I get is alpha 1 C1, alpha 2 C2, plus alpha n Cn. I add all of those up. But that's something that I knew that was 0. So what I got was that AD is 0. So what does that mean? Well, that means that D is in the null space of A. If you take a matrix, D, multiplied by A, and you get 0, then D is a solution to AX equals 0. D is in the null space of A. Well, we just proved earlier that null space of A is the same as null space of B because they're row equivalent. And so we're bootstrapping our knowledge about null space to prove something about column space. Okay, so these also in the null space of B. What does that mean? Well, that means that B times D is 0. But what's B times Z? Again, we are multiplying a matrix by a column vector. So we get a linear combination of the columns, but this time of B, and with the scalars coming from the column vector. And so that means that BD is alpha 1 C1 prime plus alpha 2 C2 prime plus alpha n Cn prime. But we said BD is 0. So what we just got is that this alpha 1 C1 prime plus alpha 2 C2 prime plus alpha n Cn prime is also 0. That's what we got. So we started with assuming that alpha 1 C1 plus alpha n Cn is 0, and we got that same linear combination of the columns of B was also 0. So if I take away our argument, what we're left with is that if you have two row equivalent matrices, and if you write down their columns, and if you have some linear combination of the columns of A equals 0, the same linear combination of columns of B will also be 0. And of course, the converse will be true, because if A is row equivalent to B, B is also row equivalent to A. Okay, so now what I'm going to do is I'm going to write this as a theorem. So A and B are n by n matrices. The columns of A is C1 through Cn. I'm just repeating myself. I already gave you the argument, but I'm just writing it down now. And B is C1 prime through Cn prime. Those are the columns of B. B is also n by n. And assume that A and B are row equivalent. Then what we know is that for scalars alpha 1 through alpha n, we have that this linear combination of the columns of A is 0, if and only if that same linear combination of columns of B is 0. So the relations between the columns of A and columns of B stay the same. So let's look at it. So here's a corollary of it. So if you have row equivalent matrices, then what if a set of columns, like maybe column 1, 3, and 5, are linearly independent in A? Well, then that means that the only linear relation among them is that if you multiply this by 0, that by 0, and by that 0, that's the only way you're going to get 0. And that means that that same thing is true of columns of 1, 3, and 5 of B. And so the corresponding set of column vectors of B will also be linearly independent. So if you find that the first, third, and eighth column of A is linearly independent, then first, third, eighth column of B will be also linearly independent, and vice versa. If you find the 47th and 48th column of B are linearly independent, the same thing is true of the 47th and 48th column of A. Okay, and because of that, because columns of A are spanning sets for the column space of A, and columns of B are a spanning set for the columns of B, because the linear independent ones correspond to each other, so will the basis. So if you have a set of vectors and you know that's a basis for the column space of A, the same set of vectors, the same corresponding set of vectors, not the same vectors, but this corresponding set of column vectors in B will be a basis for column space of B. And what do I mean by corresponding? I mean the same number. Like if the first one, the third one, and the eighth one together form a basis for column space of A, then the first one, third one, and eighth one of B form a basis for the column space of B as well. So here's one example. We'll see a couple of examples. So here's an example for column space. So A is this 4 by 5 matrix. And I find its reduced echelon form, and I get this. So what can I say about its column space? The column space of A and column space of B are not the same, definitely. But I might ask, so I'm going over everything. What's the basis for the row space of A? And we say, well, the row space of A is the same as row space of B, and therefore I can just look at B and read that the first two rows of B are a basis for row space of B, and they must be a basis for row space of A. And so I'm done there. First two rows of B are a basis for the row space of A. So rows of B are a basis for row space of A. I don't know which rows of A are a basis necessarily, but I know that these two guys give me a basis for a row space of A. Now, what is the basis for the column space of A? Now here, I can come to B also, and I say, look, the first column and the third column clearly are a basis for the column space of B. But those columns are not a basis for the column space of A, because column spaces are different. But because the first and the third columns were a basis for column space of B, the first and the third columns of A are a basis for column space of A. So again, repeating myself, first and third column of B are basis for column space of B, and that means that first and third column of A are a basis for column space of A. Okay, so now let's do another example. I'm going to tell you a bunch of vectors. The actual numbers don't really matter. I'm going to give you 5 vectors in R6. So the first one is 1, 2, 3, 4, 5, 6. The second one is 3, 4, minus 1, 2, 8, minus 3. The third one is 4, 1, minus 2, 2, 0, 1. And the fourth one is 2, minus 1, 2, 4, minus 3, and 10, I believe. And the fifth one is 6, 0, 0, 6, minus 3, 11. So these are also random things. And then what do I want to do with them? Well, these are 5 vectors in R6. And you can write them as column vectors or as row vectors, whichever way you want. These are elements of R6. And here I wrote them as row vectors. Usually I like to write them as column vectors. It would just be quite messy on the slide if I did that. So I'm writing them as row vectors. This set of vectors is a subset of R6. So we can find its span. Now the span of a set of vectors is always a subspace. So W is a subspace of R6. And we may ask questions about it, questions that we've been asking from vector spaces in general. So we might ask, what kinds of questions we might ask? We might ask, what's a basis for W? We might ask, is V4 a linear combination of V1, V2, and V3? So that's another question we might ask. We might ask, is this vector 2, 5, 6, 1, 0, 5 in W? None of those questions are terribly difficult to answer, but they're all very annoying, given the fact that these are not sort of nice vectors and they're not small. There's quite a few of them. Doing this by hand would be sort of a pain. I mean, in fact, and this is a proof of concept. What if you had, 3,000 vectors in R 4500? And that does happen often, and you might want to ask the same kinds of questions. Okay, so let's take a seat back and let's think about this sort of a little bit more conceptually before we get our hands dirty and try to answer those kinds of questions. So we have W is the span of S, and S is a set of 5 vectors in R6. So I could make a matrix out of those vectors, and I could put those vectors as rows. And I'm writing V1 through V5 because I originally wrote V1 through V5 as row vectors. So V1 is a row, V2 is a row, V3 is a row, and so on. There's 5 rows, and each of them is in R6, so 6 columns. This is a 5 by 6 matrix. So I could do that. I just put them all in rows. And at that point, I could find reduced row echelon form of A. And why would that be useful? Well, because W, the span of S, is actually the row space of A. And if I find reduced row echelon form of A, that will help me find the row information about row space of A. Or vice versa, I could look at A transpose, which means that I put all those vectors as column vectors. So I wrote V1 transpose because V1 originally was a row vector, and now it's a column vector. And so I'm writing them as columns of a matrix. And then I could find, so this is the transpose of the original one. And then what I can do is I can find reduced row echelon form of A transpose and try to see what that tells me about the columns of A transpose. And so each one of these gives us different kinds of information. And so W, the subspace that I was interested, the subspace of R6 that I was interested in, is a row space of A, but it's also the column space of A transpose. And these give me complementary information about W, but the row reduced form of A and reduced row echelon form of A transpose, as we shall see. This is an example of when matrices and understanding matrix spaces is taking us back and helping us understand subspaces, span, linear independence, and so on in Rn, in vector space Rn. So again, if you have not been looking at my videos regarding linear algebra earlier on about vector spaces and span and bases and so forth, you need to go to that for this to make much sense. Okay, so let's do that. So the first thing I want to do is using row space. So I'm going to write again a matrix A, and the rows of that going to be those 5 vectors of interest. So there it is again. And this time I'm going to find its reduced row echelon form, and I got some computer to do that for me. Almost every math computer program worth its name has a good procedure for finding reduced row echelon form. If you use things like MATLAB or other numerical or R or numerical software, they will give you sort of decimals. If you use symbolic algebra systems like Mathematical or Maple or Sage Math, then you can get things like fractions and so forth, like precise answers. So this is the reduced form echelon form of A. So what? Well, then I can say that W, the subspace of interest, is the row space of A, but row space of A is the same as row space of reduced echelon form of A. This is a typo. This should not be A transpose. It's just A. Yes, and so I can write a basis for A for W. So a basis for W is going to be which row space of reduced row echelon form of A. What are the basis for it? It's the first 3 rows. Again, the rows that have a leading one, those leading ones are going to be in a place where everything else has zeros, so they will be linearly independent. And so I will have those 3, and I find a basis for row space of A. And again, this is row space of the reduced row echelon form of A, not A transpose. This is a typo. That transpose there should not be there. Okay, and because of that, I can actually write down what W is. This is a basis for it. So alpha times this plus beta times that plus gamma times that tells me all the elements of W. And here also I should put parentheses around alpha and gamma at the end, and that's another typo. And so the advantage of this, I didn't find out which one of V1, V2, V3, V5 was a basis for the row space of A or for W, but I found these new vectors that gave me a basis for the row space of A. And the point is that this is actually sort of a nice basis, because some questions like is 256105 in W or not, it's not so easy to answer using V1 through V5, but it is very easy to answer using this new description of W, because this says the first entry can be anything you like, the second entry can be anything you like, the third entry can be anything you like, but the fourth entry has to be the sum of the first and the third. And here I can just check that, and that's not the case, and so I say no. And in fact, any vector that walks through the door and you want to check if it's in W, you don't care about what the 3 first entries are, but then you check is the next 3 entries follow these rules, and you can decide that. So this is sort of a nice basis for W. It's not the vectors V1 through V5, but it's sort of a nicer vectors because they have a lot of zeros, and it's a basis. Okay. Now let's try to use the column space. So this time I'm looking at A transpose, and I'm writing V1 through V5 as columns of A transpose, and I'm going to find its reduced echelon form, and I'm saying that the column space of A transpose is not the same as the column space of the reduced row echelon form. We know that, so that's not going to be helpful, but we know that we see that the first 3 columns of reduced row echelon form of A transpose form a basis for its column space. So the first 3 columns of A transpose are going to be a basis for its column space, but that column space is W. And so now I know that V1, V2, and V3 are a basis for W. So if you didn't like the other basis that the row space gave us, which was sort of a nice basis with zeros and things, but it wasn't elements of V1 through V5, and you said, well, I really like these vectors, I want 3 of them to give me a basis. Now you know that V1, V2, V3 are a basis for W. But more than that, you can read from here that V4, the fourth column in the reduced row echelon form of A transpose, is the first one minus the second one plus the third one. And so the same thing has to be true about the columns of A transpose. And so you now know that V4 is V1 minus V2 plus V3 without any calculation other than finding this reduced row echelon form, which was, as I said, a computer can do for you. And likewise, V5 is V1 minus V2 plus 2V3. That's very easy to read from reduced row echelon form of A transpose, but now that will be also true of the columns of A transpose. And so we have that relation too, and then other relations as well. So that's the end of this lecture. Hope to see you in future lectures. Again, in this lecture, what we did was find what the effect of elementary row operations are on matrix spaces.